a virtual method table, virtual function table, virtual call table, dispatch table, vtable, or vtable is a mechanism used in a programming language to support dynamic dispatch. Whenever a class defines a virtual function, most compilers add a hidden member variable to the class which points to an array of pointers to functions called the virtual method table. At runtime these pointers will be set to point to the right function, because at compile time, it is not yet known if the base function is to be called or a derived one implemented by a class that inherits from the base class. Suppose a program contains several classes in an inheritance hierarchy, a superclass, cat, and two subclasses, house cat and lion. Class cat defines a virtual function named speak, so its subclasses may provide an appropriate implementation. When the program calls the speak method on a cat pointer, the calling code must be able to determine which implementation to call, depending on the actual type of object that is pointed to. Because the type of object pointed to by the cat pointer is not determined at compile time, the decision as to which branch to take cannot be decided at compile time. There are a variety of different ways to implement such dynamic dispatch, but the vtable solution is especially common among C++ and related languages. Languages which separate the programmatic interface of objects from the implementation, like Visual Basic and Delphi, also tend to use the vtable approach, because it allows objects to use a different implementation simply by using a different set of method pointers. Implementation: an object's dispatch table will contain the addresses of the object's dynamically bound methods. Method calls are performed by fetching the method's address from the object's dispatch table. The dispatch table is the same for all objects belonging to the same class, and is therefore typically shared between them. Objects belonging to type-compatible classes will have dispatch tables with the same layout. The address of a given method will appear at the same offset for all type-compatible classes. Thus, fetching the method's address from a given dispatch table offset will get the method corresponding to the object's actual class. The C++ standards do not mandate exactly how dynamic dispatch must be implemented, but compilers generally use minor variations on the same basic model. Typically, the compiler creates a separate vtable for each class. When an object is created, a pointer to this vtable, called the virtual table pointer, pointer or vptr, is added as a hidden member of this object. As such, the compiler must also generate hidden code in the constructor of each class to initialize a new object's pointer to the address of its class's vtable. Many compilers place the pointer as the last member of the object. Other compilers place the pointer as the first member of the object. Portable source code works either way. For example, G++ previously placed the pointer at the end of the object. Example: consider the following class declarations in C++ syntax. Used to derive the following class. And the following piece of C++ code. G++ 3.4.6 from GCC produces the following 32-bit memory layout for the object B2. B2, plus 0, pointer to virtual method table of B2, plus 4, value of int in B2. Virtual method table of B2, plus 0, B2F2. And the following memory layout for the object D. D, plus 0, pointer to virtual method the table of D, plus 4. Value of int in B1, plus 8, pointer to virtual method the table of D, plus 12, value of int in B2, plus 16, value of int in D. Total size, 20 bytes. Virtual method the table of D, plus 0, B1F1 B1F1 is not overridden. Virtual method the table of D, plus 0, DF2 B2F2 is overridden by DF2. Note that those functions not carrying the keyword virtual in their declaration and D do not generally appear in the vtable. There are exceptions for special cases as posed by default constructor. Overriding of the method F2 in class D is implemented by duplicating the virtual method the table of B2 and replacing the pointer to B2F2 with a pointer to DF2. Multiple inheritance in Thunks. The G++ compiler implements the multiple inheritance of the classes B1 and B2 in class D using two virtual method tables, one for each base class. This leads to the necessity for pointer fixups, also called thunks, when casting. consider the following C++ code. While D and B1 will point to the same memory location after execution of this code, B2 will point to the location D+8. Thus, B2 points to the region within D which looks like an instance of B2, that is, has the same memory layout as an instance of B2. Invocation: a call to df1 is handled by dereferencing D's db1 pointer, looking up the f1 entry in the vtable, and then dereferencing that pointer to call the code. In the case of single inheritance, if the v pointer is always the first element in D, this reduces to the following pseudo C++, where D refers to the virtual method the table of D and 0 refers to the first method in the vtable. The parameter D becomes the this pointer to the object. In the more general case, calling B1 F1 or df2 is more complicated. The call to df1 passes a B1 pointer as a parameter. The call to df2 passes a B2 pointer as a parameter. This second call requires a fix-up to produce the correct pointer. It is impossible to call B2F2 since it has been overwritten in D's implementation. The location of B2F2 is not in the vtable for D. By comparison, a call to DFO is much simpler. Efficiency: a virtual call requires at least an extra index dereference, and sometimes a fix-up addition, compared to a non-virtual call, which is simply a jump to a compiled-in pointer. Therefore, calling virtual functions is inherently slower than calling non-virtual functions. An experiment done in 1996 indicates that approximately 13% of execution time is spent simply dispatching to the correct function, though the overhead can be as high as 50%. The cost of virtual functions may not be so high on modern CPU architectures due to much larger caches and better branch prediction. Furthermore, in environments where JIT compilation is not in use, virtual function calls usually cannot be inlined. In certain cases it may be possible for the compiler to perform a process known as virtualization in which, for instance, the lookup and indirect call are replaced with a conditional execution of each inlined body, but such optimizations are not common. To avoid this overhead, compilers usually avoid using vtables whenever the call can be resolved at compile time. Thus, the call to F1 above may not require a vtable lookup because the compiler may be able to tell that D can only hold a D at this point, and D does not override F1. Or the compiler may be able to detect that there are no subclasses of B1 anywhere in the program that override F1. The call to B1 F1 or B2 F2 will probably not require a vtable lookup because the implementation is specified explicitly. Something that should be noted is however that a virtual call is a conditional expression. If the virtual call is removed by removing the inheritance structure, then the decision about which function to call still needs to be evaluated in code. This will require evaluation code at each position of the code where the class is used, so dynamic dispatch isn't really a performance overhead and actually reduces code size compared to not using it. Comparison with alternatives: the vtable is generally a good performance trade-off to achieve dynamic dispatch, but there are alternatives, such as binary tree dispatch, with higher performance but different costs. However, vtables only allow for single dispatch on the special this parameter, in contrast to multiple dispatch, where the types of all parameters can be taken into account in dispatching. Vtables also only work if dispatching is constrained to a known set of methods, so they can be placed in a simple array built at compile time, in contrast to duck typing languages. Languages that provide either or both of these features often dispatch by looking up a string in a hash table, or some other equivalent method. There are a variety of techniques to make this faster. See also, virtual function, virtual inheritance, branch table. Notes: G++ SFDUMP class hierarchy argument can be used to dump virtual method the tables for manual inspection. For AIX Visual HXLC compiler, use QDUMP class hierarchy to dump class hierarchy and virtual function table layout. References: Margaret A. Ellis and Jan Strostrup, The Annotated C++ Reference Manual. Reading Massachusetts, Addison Wesley. Ellis and Strostrup 1990, pages 227–232, Danny Karlov. C++ Reference Guide. The Object Model 2. 2003. Heading Inheritance and Polymorphism, and Multiple Inheritance. C++ ABI closed issues at the Wayback Machine, Drizzen, Carroll and Har. Paragraph LZLE, as, the direct cost of virtual function calls in C++, Oopsla 1996, Zendra, Olivier and Drizzen, Carroll, Stress Testing Control Structures for Dynamic Dispatch in Java, pages 105-118, Proceedings of the Usenix Second Java Virtual Machine Research and Technology Symposium, 2002.